Hi, I'm here to talk about visual objects, their emergence and representation. Before I do so, I'd like to acknowledge my collaborators whose work I will connect through the arc of this talk. Now, when thinking about visual objects, we think of pieces of an image we give names to. And as a reminder, while much of your brain is devoted to processing visual information, about half of your cortex if you're a macaque monkey is shown here in color, language emerged very late in the evolutionary tree. Does it mean that visual objects are a concept restricted to humans? Well, not necessarily. You may argue that cats can reason, and plenty of YouTube videos will illustrate that. And similarly, dogs can talk, as Gary Larson pointed out in The Far Side. Nonetheless, if language was essential, then visual objects would be restricted to a relatively small branch of the phylogenetic tree. Now, you could argue that evolution is irrelevant. We didn't build the airplane by imitating birds, at least not very successfully. And while language appears at the end of the evolutionary tree, once we have it, we can work backwards and use it to facilitate the representation of objects. So that's certainly a valid viewpoint. But even if you take that, it's worth reminding that language, which is a human construct, so its complexity cannot exceed the union of the capacity of human brains or the corpus of written text. Apparently, that requires a very small capacity to be represented, about 1.5 megabytes in humans. Contrast that with the complexity of the physical world, which is effectively infinite. When you look out the window, you can see all the way to the moon. With this context in mind, let's start our journey through visual objects. There is a rich literature on the topic, but a few attempts at the definition. And of course, the definition is implicit in the method or the benchmark, and it basically boils down to subsets of pixels in an image that somehow relate to other pixels in different images to which humans have attached some label. And related could be measured by similarity, measured by, for instance, linear product of some function phi that could be implemented by deep neural networks and maps it to some vector space. And close could be to the average of objects that have the same label in a finite training set D. Okay. But if that's the case, does it mean that there cannot be visual object without humans, without language? I think you'll be hard-pressed to argue that the dog does not have a concept of bone in his head, and that is manifest visually. Okay, you could say dogs have language, but what about dinosaurs? Of course, we don't know, but it's unlikely that dinosaurs went extinct because they did not have enough annotators. So the first point I would like to make is that visual objects exist in the scene, not in the image. They're just manifest through the images, but there are no objects in images, just pixels. This is not a new idea. In the 50s, Gibson talked about detached objects as layout of surfaces surrounded by the medium. And those are relevant because you can grab them, eat them, and so on. But since you don't see many objects floating in midair, a weaker notion introduced in 2012 was that of a detachable object as a layout of surfaces partially surrounded by the medium. And that is relevant because relative motion triggers occlusions, and occlusions are manifest in the image, but they're informative of the topology of the scene. It tells you whether two nearby points in the image are actually neighbors in the scene. And they can be arbitrarily far. You look out the window and one pixel sees the moon, and the nearby pixel sees the window frame. Right? So how does this definition impact the way we learn objects? Well, for once, portions of the scene that cannot be detached are not objects per se. They may be images of objects, for instance, painted on the ground, but a properly designed system bootstrapped from blank slate should find things like the car that sticks out of the ground, but has no basis to find the girl, unless it has seen girls sticking out of the ground before. So here we're talking about a primordial system where it starts from blank slate, like a deep neural network before you start training. But there may be some architectural biases and other inductive biases. So objects exist in the scene. And the second point I would like to make is that you do not need labels or names or interpretations or semantic to discover them or to detect them. This is also not a new idea. Bela Ulesh in the 60s made this point compellingly by removing from the images all their pictorial content. So there is nothing to understand or interpret in the images. But as soon as time flows, you can clearly see objects emerge, whether or not you have names for them. Okay, you can see here the importance of occlusions again. Of course, once things move and you detect them, you can then store them in memory and then retrieve them in the future, even from a static picture. And that's the idea behind dynamic static bootstrapping that I will come to later. And here there's no supervision but time. But I argue, in addition to motion being fundamental, I also argue that there's an independent reason for the necessity of motion. So if all you see is different images, each of a different scene, since the scene is infinitely more complex than the image, you cannot possibly learn that there even exists a scene. You can just capture patterns and regularities in the images. But then again, there are no objects in images, just pixels. And again, things do not need to keep moving in order for you to see them, like the dinosaur visual system. Once moved, you can learn a model, and then you can use that to detect them in static images. Next, I like to turn these ideas, that objects exist in the scene, that they need to move, that occlusions inform the partition of the image based on the topology of the scene, into variational principles that you can use for learning. Okay? And also later, I would like to ask the question, well, since objects exist in the scene, is there a true scene? Is there a physical scene? What is that? Can I learn that? And how? And do nerves have to do with that? So the first concept I'd like to present to you is this idea of contextual information separation, which was introduced by Yang and Loquecho and other in CVPR 2019. So imagine you have an object, for instance, the blue square, which occludes part of the scene, let's call it the background, everything else which is not the object, its complement. If you have seen scenes like this before, you could hallucinate what's behind the occluder. Okay, this is a transductive version of this called in-painting. You use the pixels outside the blue region to fill in the blue region. Let's say this is not the true object. And so you would imagine, it mostly yellow and blue. But let's say that this thing is not the true object, but just your hypothesis of the object. And let's say that here's a different hypothesis for the object. Okay. If this is your hypothesis, then you will do a much better job at filling in not just hay and sky, but also the zebra and all. Right. And similarly, if this is your hypothesis for the object, you could fill in the background with a zebra, and you will do something. But if I give you this hypothesis for the object, you will do a much better job at completing the outside. Right? So different hypotheses will yield different quality in the reconstruction of the segment of an image given its complement. Okay? And the hypothesis that gives you the worst possible reconstruction is the one that makes the foreground and the background uninformative of each other. They're independent in some sense. And so those are the objects. So once projected on the image, they make the inside of the image as uninformative as possible as of the outside, and vice versa. Okay? So concretely, if this is the hypothesis, you can reconstruct its complement pretty well, right? It looks plausible. Okay? But if this is the hypothesis, and it coincides with the boundary of the object, now your reconstruction doesn't know anything about blacks and whites, and it will reconstruct with blue and yellow. Okay, so this concept translates naturally into an adversarial loss function where an in-painter, for instance, implemented by a trainable module or a deep neural network, tries to fill in the complement as well as possible, while the region is chosen so that the reconstruction is as bad as possible. So here is U is any function of the image, for instance, the gray level or the color values or the optical flow or a histograms of filters. And this is a mask that masks the inside. And so you're going to try to explain the inside using the outside and explain the outside using the inside, normalize somehow. And you're going to optimize this by trying to in-paint as well as possible. And at the same time, trying to make the in-painting as poor as possible. And by doing that, you should converge to the object. Okay. Now, there is an information theoretic interpretation as the principle looks for regions that are as uninformative of their complement as possible. And this is called the contextual information separation principle. And it can be applied to any function U of the image, for instance, grayscale, color, optical flow, histograms of statistics, your choice. The first term tries to explain or compute the entropy of inside a mask M given the image or the function of the image outside, normalized by the uncertainty inside. And the second term tries to do the same for the complement. Okay. Now, for those of you who remember it, this approach is reminiscent of the classic Mumford-Shaw functional, but it's backward. Mumford-Shaw tries to explain the inside of a region of an image using only pixels inside that region, and so for the outside. Now, the obvious solution is that phi is the identity. So you need to enforce regularization, like smoothness of a statistic phi or of the boundary. Here, we do the opposite. Instead of trying to model a region as well as possible using pixels inside that region, we try to model the region as poorly as possible using only pixels outside that region. Obviously, you need memory to do that. Okay, so you can think of contextual information separation as the inductive version of the Mumford-Shah functional. The advantage is generalizability. Whereas in Mumford-Shah, for every new image, you have to solve an optimization problem anew. Here, you do it once during training. Right? At that inference time, you just feed-forward, you compute a function. Now, another interpretation of contextual information separation is the visual analog of masked autoencoding that's popular in languages, except that here the mask is the object of inference rather than a manually concocted occluder, as in self-supervised learning. So in language, the boundary of objects and the object of inference correspond because they're only discrete characters, not shapes. And here are some examples and numbers that show that CIS works when applied to motion statistic, that is when U is optical flow. But I find it more useful to consider when CIS does not work. Okay. For instance, if you try to apply directly to the pixel in a static images, like the random dot stereogram of Uresh or this mountain goat, it cannot work because there is no separation between objects and the background, often by evolutionary pressure. Of course, motion can help, but even in this case, the camera is moving. And more importantly, the temporal reinforcement from repeated observation, knowing that you're looking at the same scene, should help. And this is the key idea of DysTaB. You start with a clean slate, and as soon as you detect objects, you can feed them to a time-supervised detector that trains a static module that then improves the in-painter inductively, which then improves the discovery of objects until you've captured the world, or at least the world that at some point or another stands out or moves. And here's an example, but much more work is needed in this area with many contributors to this progress, including in this workshop. Another important aspect of DysTaB and modeling objects in the scene is that you can integrate multiple sensory channels. I've shown the case of motion and color for DysTaB, but you can also have vestibular sensors like inertials, accelerometers, gyromagnetometers. Then in that case, you can maintain a metric representation of the world. In this older demo that was shown live at CVPR 2017, Jingmin Dong, Konstantin Tsotso, Shahan Fei, and others have shown that even though visually indiscriminable, a proper object representation can distinguish between a toy car and a real car, since they have an indirect measurement of scale from visual inertial odometry. Okay. And the same goes with occlusion. Even when not visible, previously seen objects are known to persist, and so you can retain them in memory and predict when and where they will be visible again. So in this case, the chair becomes occluded by the monitor, but you know it's still there. And scale and occlusion are the two most challenging phenomenology in image formation, so visual object representation should account for them in a fundamental way. Now, I think that some of these ideas I talked about should be fairly uncontroversial. Objects in the scene, they are primed by motion, they can be bootstrapped and thence represented statically, multisensory validation, have persistence and scale, and so on. But I have used the term information and informative in reference to images that are measured, or training data, which sits in memory. And I think it's important to know that when you try to be more precise about what information means in the context of inductive learning, things can get very tricky. So I want to spend a few minutes giving you a sense of what's behind the word information, as I say. So as a reminder, in communication, information is a property of a distribution of random variable. An anecdote is that Robert Fano, talking to a group of us gathered at a workshop, reminded us that Wiener once walked into his office where he and a few fellow graduate students were working and stated nonchalantly that information is entropy, and then left, which left everybody puzzled, and so they had to go look into it, and that the rest of the history of information theory. But here, there are no random variables. There are images and there are data sets. They have zero entropy. Now, whatever information means for an inductive system, it's in the data set. There's nothing else known to the model before you start training. And after you're done training, whatever information was in the data set is now in the weights of the trained model, which are also fixed, typically. Okay? And so the fact is that there is no random variable. You have one data set and one set of weights, so technically speaking, there is zero information. And even if you treat dataset and weights as random variable, because a trained neural network is a deterministic system, it has infinite differential mutual information. So either way, classical notions of information from communication theory don't really make sense in the context of inductive learning. But the notion of information that the weights, which is what's left after training, contain about the dataset, which is what you have before training, appears everywhere in inductive learning. And this is an example in the generalization bound. So you would like to be able to say that your model works well for test data, which you haven't yet seen, so you cannot compute this number, the test loss. But you can compute the training loss, which is what you optimize, and you would like to bound the test error with the training loss plus something. And that something, in a variety of bounds, this is one of them, shows up as the information that the weights contain about the dataset. Okay. So as I said, for a deterministic trained neural network, this number is infinity. So what these bounds tell you is that the test error is less than the training error plus infinity, which is not very useful. Okay. And so let me tell you another way in which this notion of Shannon classical mutual information doesn't make sense for trained models, even if you could compute it, even if you had a distribution of data set and a distribution of weights. So take your trained deep neural network. It has a bunch of weights that are sitting in memory. And now take the data set and append each datum to a weight. Okay, typically you have more weights than data, and so you can just store your entire data set after the least significant bit. So now the information in the weights, as their coding length measured somehow, has increased, okay, by the volume of the data set. But do you expect that your trained network will work any better on test data? Probably not, right? So this information, whatever that means, is really inaccessible. You cannot do anything with it unless you see the data again, which you will not by the inductive hypothesis. So what is the quantity here that you should put in the, for instance, generalization bound that you can actually compute for a trained network with a fixed data set and after it's converged to a fixed set of weights? Okay. Now, it turns out that Shannon gave us some hints on how to do that, at least for communication. And so the idea was that he was trying to measure the entropy of the English language. So he took let's say, a segment of text, and then he added noise. You can think of removing, if you want to think about masked autoencoding, some letters or words, and then ask people to fill in the words. Okay, and if you can fill in the words exactly 100% of the time, well, that word did not contain a lot of information. You might as well not store it or replace it by noise or empty. Okay, but if a word or a character was so ambiguous that different people guessed different things, then you would want to store that with many bits and use that to compute the entropy of the English language. Now, for communication, that's easy because the task is the same as the data set. Here comes a message and you want to transmit it and replicate it at the destination. For us, this is different because we're not interested in the data. We'll never see the training data again. We're interested in data we haven't yet seen. And so this is another ingredient comes to play here, which is the performance you desire in the task. Okay, let me give you an example. Suppose that your task is to classify airplanes from cartoon characters. Okay, binary classification. Let's say the dataset is balanced, and so are training test samples. So if you're okay with 50% performance, then you don't need any information stored in the weight. You just say cartoon characters every time, and you're wrong 50% of the time. Okay, and even if you're okay with 75%, let's say, error, you could just store a color histogram, and if there's a lot of blue, you say airplane, and otherwise you say cartoon character. And that representation is robust to noise. So even if you perturb the data a little bit, you still get 75% correct. But if I now say 75% is not good enough, I want 99.9% correct. And by the way, perturbing the data or perturbing the model is dual, at least in the first layer of deep networks. But if, again, I want 99.9% correct, now I have to account for the fact that there may be planes with cartoon characters painted on them. And the moment I perturb the data or the model, I will make errors. Okay, and so the representation I need is substantially different. Okay, so how do I turn this into a measurable expression for the information in the weight, the accessible information in the weights. Okay, and here's the idea, which you can find in a paper titled "Where is Information in a Deep Neural Network?" So you start with a deep neural network and train it to converges and get a set of weights. It doesn't matter how you train it. You could have been trained it with stochastic gradient descent, deterministic gradient descent. Really doesn't matter. Get a set of weights. Okay. Now take those weights and perturb them however you want. Okay. You add noise to them, for instance, sampling it from a certain distribution with a certain covariance along all directions. And again, this is your choice. This is a feature, not a bug. You pick the distribution of noise, and that's essentially the unit by which you measure information. And also, you pick a threshold, okay, a performance threshold. That's, again, a feature, not a bug. It's a control parameter you have. So now, the amount of noise that you can add to the weights that keeps the training loss, which you can measure, below your threshold tau, is obviously information variability that is useless to you because the network doesn't see it. Okay, it's hidden behind the function that computes it. And so this is the irrelevant information or the useless information. So it's the maximum amount of noise you can add, which you can compute because you choose the noise distribution, that doesn't damage the training loss, which you can measure. Okay. Now, whatever information was in the dataset before you started training, that's a constant, you don't get to touch that. That would be, the difference from that would be what's left. That's the residual information which is accessible by the model. So this is the definition of accessible information. It's what's left after you remove, or after you add noise to the point where your network doesn't see an effect. Okay. Now, this is an optimization problem constraint. You can turn it into its Lagrangian form, and the second order approximation of that tells you that this is related to the log determinant of the Fisher information matrix. And that has a lot of connection also to stability of training, curvature of the loss landscape, and other things that I don't have time to get into. But the bottom line is that the definition of information in a trained network has associated with it a Lagrangian, and this Lagrangian is a variational principle that you can use for training that will yield maximum generalization. Okay, and this Lagrangian is called the information Lagrangian. It was introduced in 2018 in this paper, Emergence of Invariance and Disentanglement in Deep Representation. It looks like an information bottleneck, but it's not the information bottleneck that's talked about in papers about the information bottleneck. That pertains about the activations of the network given test data. This pertains about the test training loss, the data set, and the weights. Okay, and again, to second order, this is approximated by the Fisher information. And of course, you don't need to technically add noise. Okay, conceptually, you can just compute it. But the beauty is that SGD actually puts noise there for you during training. So all you need to do is you need to store the last gradient vector before you stop training. Okay. So what is new here? So there is a definition of information that can be measured by the size of the maximum perturbation that you could apply to the weights, you don't technically apply it, without incurring a training cost. This is well defined, whether or not you have deterministic model or stochastic model like a Bayesian neural network, whether it's trained on a single data set or on a distribution of data set, whether it's trained with stochastic gradient descent or deterministic gradient descent. Associated with this information, there is an inductive principle, which is the information Lagrangian, and this relates to Fisher information and is computable for real-world deep networks, not in the trillions of parameters, but in the many millions, not just toy problems. And this also yields generalization bounds that are non-vacuous. As a small aside, since I talked about biology, now that we have a computable measure of information, which you can compute per weight, per layer, per network, you can actually see how it evolves during the training process, because the Fisher is attached to the trajectory, not just the final convergence point. And so if you do that across a variety of training sets and architectures, this is done for ResNet 18 on CIFAR10, what you can see is that at the beginning, the amount of information stored in the weight goes up as if you're memorizing the data set, and then it starts coming down. So literally you are forgetting the data, and then it converts to a steady state. And this forgetting happens while your performance in the task, measured by the test accuracy here in green, keeps improving, keeps increasing. So this is very counterintuitive for information theorists who predicate that you should never throw away information. But here it appears that throwing away information is at least beneficial, if not necessary, for generalization, for learning. And just as a curiosity, fascinating curiosity, is that this curve of the feature information during training is very heavily correlated, of course, different units, days versus epochs, with the sensitivity to critical learning periods in cats. And those critical learning periods are also present in deep neural networks. Critical learning periods are phenomena where if you mess with the data during the initial phases of learning, even if you correct, for instance, if you have a visual deficit when you're born and you don't correct it early enough, doesn't matter how long you can see sharp after that, you don't learn how to see well. This is manifest in humans just as in cat and leads to amblyopia. And the sensitivity to critical period ceases after a certain age. If I take off my glasses now and put them back a month from now, I would not have any lasting impact. But if I was born with myopia and I didn't correct it early enough, I would likely never learn to see well. So hopefully you can see a rich world of exploration around the issue of memory, information, knowledge, and transferability that emerges simply from properly trying to define information that the present data contains about the scene. The scene being manifest, for instance, by a training set of data of the same scene. Okay. Now, I want to come back to the last point I mentioned in the introduction to this talk. Since objects exist in the scene, the real scene, not images of the real scene, can we actually learn the true scene, the real scene? And what does that even mean? And things get interesting pretty quickly. So the first point here to notice is that physical objects live in the continuum. Now, whether the scene is, that the world is infinite, whether it's continuous or discrete, physicists haven't told us that yet. But I can certainly move in the continuum, and even if I sample images on discrete time intervals, those intervals can land on a dense trajectory. And so I can generate every possible image, even with just one particular scene and more. Okay. Now, of course, objects can only be experienced through observation of finite data and can be stored with finite resources of memory computed over finite time. And so the question of reality is really, can we represent in our head or in the weights of a deep network scenes, which are essentially infinite objects, with discrete entities? You can call them symbols, you can call them programs. Okay? And can you represent them in a way that you really understand them, not just approximate them, okay? But can you represent the essence of an infinitely large scene with finite memory, infinite time with finite resources? Okay, this is the classical signal to symbol barrier problem. So we put a few ideas in a paper recently. You can find it on arXiv. And the first point this paper makes is that in terms of abstract concepts, which are things that are represented inside your brain, that could have an infinite manifestation. Okay, let's take, for instance, the example of pi. You have a concept of pi, and that has an infinite manifestation, an infinite number of decimals. You've never seen all of pi, right? But at some point, you get pi, you understand pi to the point where, if necessary, you can simulate the entire efflux of digits all the way to an arbitrary point. Okay. So similarly, if instead of pi, you're looking at the scene, can you get the scene? Can you understand the scene? So Gold in 1967 taught us that a deep network, didn't talk about deep networks, but we kind of translated into the language of networks, can actually understand an abstract concept, meaning that it can represent infinite time with finite memory, even though it has an infinite efflux of data. However, an external entity, for instance, you watching the deep net, cannot know when such understanding has occurred. Okay. For instance, in the case of pi, you could train the network with the digits of pi up to a point, and you can ask the network to extrapolate, but at some point it will have to stop. And how do you know that the network will not get it wrong from that point onwards? Okay. So the second point we make in this paper is that physical objects are abstract concepts. There really is no difference between pi and the physical scene. Okay. However, bad news is that A feed-forward architecture, no matter how big, no matter how trained with, no matter how many data, cannot understand physical reality. Okay. In fact, a CNN cannot even classify even from odd numbers beyond a certain size. Okay. And a multilayer perceptron, for instance, on Earth, cannot fundamentally understand physical reality. Okay. Now, for an architecture that has some type of recursion mechanism, even implicit in the data, like in a transformer, you can understand reality, but your understanding of reality needs to be constantly validated. Okay, and that requires ability to control the data acquisition process, to interact, to intervene in the environment. Okay, and this is the interaction part that I haven't elaborated in. And this is not just an academic exercise where you think about abstract concepts and pi, but there are real implications in authentication. We live in the age of deepfakes, metaverse, and other things. And so the bottom line of this talk is that the signal-to-symbol barrier can be overcome by a trained deep neural network who can interact with the environment, but we humans cannot know when such understanding has happened. And I'll leave you with a few references for those of you who are interested, and feel free to reach out to me if you have any questions or comments, and I'll be happy to respond. Thank you.